Today we're going to learn about waves. We're going to talk a little bit about their properties and their behaviors. We have three objectives for today. First, you're going to be able to describe waves for me in terms of their wavelength, their frequency, and their amplitude. Then we're going to explain three different phenomena that are observed in waves' behavior. We're going to talk about reflection, refraction, and interference. I want you to be able to explain each of those to me. And finally, we're going to be able to tell the difference between longitudinal waves and transverse waves. To start off with, let's define a wave. In science, we define a wave as a disturbance in a medium that carries energy in a regular and repeating pattern. That regular and repeating is important. We're going to be repeating over and over and over, okay? If it's jagged and noisy, it's not necessarily a wave. It's also important to note that in our definition we said medium. A medium is a substance through which a wave travels. So if your wave is traveling in the air, air is the medium. If it's in the water, water is the medium. All waves have the following properties. First, let's talk about wavelength. This is the distance between the same point on two different waves. So if we go back to our image here, from here to here is the same point on two different waves, so we would consider that our wavelength. Same thing from down here all the way to over here, or even if you picked a random point on the side of the wave, if you found the same one on the other one, that would be a wavelength. So the more energy that a wave carries, the shorter its wavelength becomes. So if you're looking at a wave with a really short wavelength, really small distance between crests, then we would consider that a high energy wave. Amplitude is the distance between a wave's midpoint and its crest or its trough. So again, looking back at our image here, from the top of the crest to the midpoint or from the bottom of the trough to the midpoint is considered the amplitude. This also changes with the amount of energy, and it's going to get taller or deeper, depending on your definition, the more energy that the wave is carrying. The last one, frequency, is the number of waves, crests or troughs, a full wavelength that passes a point in a given amount of time. Okay? So this one isn't a part of the wave that we can label here, but essentially what scientists do is they pick a point, sort of like a finish line, and they watch the waves move across that point, and they count how many wavelengths go past that point in a specific amount of time, usually a second. So this wavelength is relatively long. You're going to have a few of them pass in a second, but not a ton. But if we had a second wavelength that was much shorter, we would have many more of those pass this point during that 1 second. And so it would have a higher frequency. So the more energy that a wave carries, generally the higher its frequency is. And if we go back to our example here, okay, you'll see that there's a bit of an inversely proportional relationship between frequency and wavelength. The longer the wavelength is, the smaller the frequency is. And the shorter the wavelength is, the higher or the larger the frequency is. So important relationship there. The last property that we're going to talk about is velocity or speed, and this is different for every wave, and it's even different for the same wave depending on which medium it's traveling through. So a wave might have one speed in water and another in air, but you can always find the wave's speed by multiplying their wavelength times their frequency. There are a couple different types of waves that we're going to talk about here in a second, but I just want to give you a visual of them before we do. The first one here is longitudinal waves, and they look a little different than the waves we've been drawing because they're made up of compressed areas and expanded areas. So just like the waves with the peaks and valleys had, there's still a wavelength here. It's just measured from one area of compression to another area of compression, or from an area of expansion to another area of expansion. Still a wavelength, and our amplitude is still here from the midline to the top. The other type of wave, which we've been drawing already and you've seen a diagram of, is transverse waves. So you can see the amplitude there, you can see the wavelength there, you can see how they're moving. So what makes these two waves different from each other? And it's not just that they look different, but they also behave differently. Okay? The first type of wave that we drew is a transverse wave. This is a wave where the medium moves at right angles to the direction of the energy movement or the wave movement. So notice here that the particle is moving up and then back down, but the energy is going side to side. So you'll notice how those form a right angle. So the example they give here is that in water, the water moves up and down, but the energy is traveling side to side. And interestingly enough, the water isn't moving with the energy. Waves don't move the matter, they just move through the matter. So if you've ever seen a lake with like leaves on the surface, if you drop a pebble in, the leaves move up and down a bit, but they don't travel out away from the ripples quite as much, and that's because they're moving up and down, but the energy is moving side to side. In contrast to that, we have longitudinal waves. These are waves where the medium moves back and forth in the same direction as the energy is moving. So in this case, you have like kind of a slinky here, right? So the slinky coils move this way, and then they move back this way. And then the energy is moving in that direction, or the wave is moving in that direction. So they're kind of parallel or moving in the same plane as opposed to moving at 90-degree angles to each other. Next, we're going to talk just a little bit about wave behavior. Waves exhibit several phenomena that extend across all wave types, and we're going to cover each of them in detail. The first is reflection. This is what happens when a wave strikes a boundary and then bounces back off of that boundary. And an interesting phenomenon that we see is that the angle at which they strike the surface, which we can see either here or if you're comparing it to the normal right here, is the same angle at which they are reflected back off of the mirror. We call this the angle of incidence, which is why you'll see a little eye here, and the angle of reflection. Along with being reflected, waves can be refracted. So when a wave moves from one medium to another, we'd already discussed that that can change their speed. And if it does, then the direction of the wave is going to change just a little bit too, and it's going to be refracted. Okay, so you can see that happening here. The light comes in, it goes from being in the air out here to being in the plexiglass, and it bends up. And then the same process repeats in reverse when it transitions from the plexiglass back into the air and it bends down again. That bending is a result of a change in speed. And the last one is interference. When waves overlap with each other, they can interfere with each other, and they can either add up or they can cancel each other out. Okay, so constructive interference is when they add up. So you have two crests or two compressions that overlap, and they add up to make a compression that's twice as large. So you look over here, we've got a little wave, but it's lined up exactly with another little wave. And so these two get added together, and we wind up with a wave that's twice as tall and twice as deep as it was before. The other type is destructive interference. So this is when they're not lining up perfectly. It's actually when they're lining up oppositely. So we have the crest here, but the trough here. And essentially, since this is going the same height above and the same height below, they cancel each other out, and it winds up looking like there isn't a wave there at all. And that is destructive interference. All right, that is it for the notes for today.